Text classification is a powerful tool in the world of machine learning. It allows us to automatically categorize text data, such as documents, emails, and social media posts, into predefined categories. This technology has a wide range of applications, including spam filtering, sentiment analysis, and topic categorization. Imagine being able to instantly sort through thousands of customer reviews and identify the ones expressing negative sentiment. Or picture a system that automatically tags news articles with relevant topics, making it easier for readers to find the information they're looking for. These are just a few examples of how text classification is being used to streamline processes and gain insights from textual data. In this tutorial, we'll delve into the practical side of text classification by building a model that classifies web server response messages. Our goal is to train a model that can accurately distinguish between error and success messages, providing a simple yet effective example of how to apply this technique to real-world scenarios. Whether you're new to machine learning or looking to expand your knowledge, this tutorial will guide you through the process step by step, providing you with the tools and understanding to start building your own text classification models. Before we dive into building our text classification model, we need to set up our development environment. This involves installing the necessary Python libraries that will provide the foundation for our project. Don't worry if you're new to Python or these libraries. The installation process is straightforward. First and foremost, we'll be using TensorFlow, a powerful open source library for numerical computation and large-scale machine learning. TensorFlow provides a flexible framework for building and deploying machine learning models, including those for text classification. Alongside TensorFlow, we'll be utilizing Keras, a high-level API that runs on top of TensorFlow. Keras simplifies the process of building and training neural networks, making it more accessible to both beginners and experienced practitioners. With Keras, you can define complex models with just a few lines of code. To install these libraries, you can use pip, Python's package installer. Simply open your command prompt or terminal and execute the following commands. Pip install TensorFlow, pip install Keras. These commands will download and install the latest versions of TensorFlow and Keras, along with any required dependencies. Once the installation is complete, you'll have all the tools you need to start building your text classification model. With our toolkit ready, we can now turn our attention to the data that will fuel our text classification model. In this tutorial, our focus is on classifying web server response messages into two categories, error and success. Let's start by creating a small dataset of response messages that we'll use to train our model. This dataset will consist of pairs of messages and their corresponding labels. For simplicity, we'll represent the labels numerically, with 0 indicating an error message and 1 indicating a success message. Here's an example of how our dataset might look. Messages =, 404 not found, 200 OK, 500 internal server error, 201 created, 403 forbidden, 204 no content. Labels =, 0, 10101. In this example, each message corresponds to a specific HTTP status code, providing a clear indication of whether the request was successful or encountered an error. The messages list contains the raw text messages, while the labels list stores their corresponding numerical labels. This dataset, though small, captures the essence of our classification task. As we progress through the tutorial, we'll use this data to train a model that can generalize beyond these specific examples and accurately classify unseen response messages. Now that we have our dataset ready, the next step is to transform our text messages into a format that our neural network can understand. Neural networks, at their core, operate on numerical data. Therefore, we need to convert our text strings into sequences of numbers. This process of converting text into numerical representations is called tokenization. In essence, tokenization breaks down each text message into individual words or characters, known as tokens, and assigns a unique numerical index to each token. Keras provides a handy utility called Tokenizer that simplifies this process. Let's see how we can use it to tokenize our response messages from TensorFlow, Keras. Pre-processing, text import tokenizer, tokenizer equal sign tokenizer, tokenizer fit on texts, messages, sequences equal sign tokenizer, texts to sequences, messages, print sequences. In this code snippet, we first create an instance of the tokenizer class. We then fit the tokenizer on our list of messages, which builds a vocabulary of all the unique tokens present in our data. Finally, we use the texts underscore to underscore sequences method to convert our messages into sequences of numerical indices. The output of this code will be a list of lists, where each inner list represents a message and contains the numerical indices of the tokens in that message. This numerical representation is what will feed into our neural network. Section 5, padding, equalizing sequence lengths. You might have noticed that the tokenized sequences of our messages can have different lengths. For instance, the message 404 not found has 3 tokens, while 200 OK has only 2. However, neural networks typically require inputs of a fixed size. To address this discrepancy, we employ a technique called padding. Padding involves adding special padding tokens to shorter sequences to make them equal in length to the longest sequence in our data set. These padding tokens act as placeholders and don't carry any meaningful information. Keras provides the pad underscore sequences function to handle padding efficiently. Let's see how we can pad our tokenized sequences from TensorFlow.Keras.preprocessing. Sequence import, pad underscore sequences, padded underscore sequences equal sign, pad sequences, sequences print, padded sequences. In this code, we use the ipad underscore sequences function to pad our sequences to the length of the longest sequence in the sequences list. By default, padding is applied to the beginning of each sequence, but you can configure it to be added at the end as well. After padding, all our sequences will have the same length, ensuring that they can be fed into our neural network without any issues. This step is crucial for preparing our data for model training. Section 6. Constructing the neural network model. With our data pre-processed and ready, it's time to build the heart of our text classification system, the neural network model. We'll be using a simple yet effective architecture consisting of an embedding layer, a global average pooling layer, and a dense output layer. The embedding layer is responsible for transforming our numerical token indices into dense vector representations. These vectors capture the semantic meaning of the tokens, allowing the network to learn relationships between words. The global average pooling layer then condenses the output of the embedding layer, creating a fixed-length vector representation of the entire input sequence. Finally, the dense output layer with a sigmoid activation function produces a probability score between 0 and 1, indicating the likelihood of the input message belonging to the error or success category. Let's translate this architecture into code using Keras from TensorFlow.Keras.models import sequential from TensorFlow. Keras, layers import embedding, global average pooling, 1D dense model equals sign sequential model, add, embedding len tokenizer word index plus 116, model, add, global average pooling 1D, model, add dense, 1 activation sigmoid, print model summary. In this code, we first create a sequential model, which allows us to stack layers linearly. We then add an embedding layer specifying the size of our vocabulary and the dimensionality of the embedding vectors. The global average pooling 1D layer follows, and lastly we add the dense output layer with a sigmoid activation. This code defines the structure of our neural network model, setting the stage for training and prediction. Section 7, compilation, configuring the learning process. Before we can train our model, we need to compile it, which involves specifying the optimizer, loss function, and metrics that will guide the learning process. The optimizer determines how the model updates its weights based on the training data, while the loss function measures the model's performance on the training data. For this text classification task, we'll use the Adam optimizer, a popular choice for its efficiency and effectiveness. As for the loss function, we'll use binary underscore cross entropy, which is well suited for binary classification problems like ours. Let's compile our model with these settings. Model.compile optimizer Adam. loss equals sign, binary underscore cross-entropy, metrics and accuracy. In this code, we call the compile method on our model, passing in the optimizer, loss function, and the accuracy metric, which will allow us to track how well our model is performing during training. With the compilation step complete, our model is now ready to learn from the data. Section 8, Training the Model. Now comes the exciting part, training our model. During training, we feed our pre-processed data into the model, allowing it to learn the patterns and relationships between the input messages and their corresponding labels. We'll train our model for a certain number of epochs, which determines how many times the model will iterate over the entire training dataset. With each epoch, the model adjusts its weights to minimize the loss function and improve its accuracy. Let's train our model using the fit method. Model, fit padded, sequences, labels, epochs, equals sign 10. In this code, we call the fit method, providing our padded sequences as input and the corresponding labels as the target output. We set the number of epochs to 10, meaning the model will go through the entire dataset 10 times during training. As the training progresses, you'll see the loss and accuracy metrics being printed, giving you insights into how well the model is learning. Section 9, Making Predictions. With our model trained, it's time to put it to the test and use it to classify new unseen response messages. Let's say we have a new message, 502 bad gateway. We want to know whether our model classifies it as an error or success message. To do this, we need to pre-process this new message in the same way we did with our training data, tokenization and padding. Once pre-processed, we can feed it into our model using the predict method, which will output a probability score. Here's how it looks in code: new underscore message, equal sign 502 bad gateway, new underscore sequence, equal sign tokenizer, text to sequences, new message, new underscore padded underscore sequence, equal sign pad underscore sequences, new underscore sequence, maxlint padded sequences dot shape 1. Prediction equal sign model, predict new padded sequence, if prediction. 0.5, print success, else print error. In this code, we first pre-process the new message, then use the predict method to obtain the probability score. Based on a threshold of 0.5, we classify the message as success if the probability is above the threshold and error otherwise. This demonstrates how to use our trained model to make predictions on new data, putting our text classification system into action. Section 10. Evaluating model performance. While training accuracy gives us an idea of how well our model learned from the training data, it's crucial to evaluate its performance on a separate, unseen dataset called the validation set. This helps us assess how well our model generalizes to new data and avoids overfitting, where the model performs well on training data but poorly on new data. We can split our initial dataset into training and validation sets, using the validation set exclusively for evaluation. During training, we can monitor the validation accuracy along with the training accuracy to detect any signs of overfitting. Keras allows us to pass in a validation set to the fit method, which will automatically evaluate the model on the validation data after each epoch. This provides valuable insights into the model's generalization ability. By evaluating our model on a separate validation set, we gain a more realistic understanding of its performance and can make more informed decisions about its deployment and potential improvements.